Hello, I'm Mr. Craig, and I wish to work out a few of these problems on the molecular geometry worksheet. Let's read the instructions first. In the spaces provided, first calculate the number of valence electrons, then draw the electron dot or Lewis dot structure, then determine the geometry with the lone pairs of electrons, and then the molecular geometry, the name and the shape that the atoms alone form. Finally, determine whether the molecule is a polar molecule or a nonpolar molecule. All right, well, let's go ahead and get started here. I may blow this up just a little bit so it's a little easier to see. Actually, yeah, let's do that. So I have the columns, which are number of valence electrons, the Lewis structure, the geometry with the lone pairs, and the molecular geometry, the shape that the atoms alone form, and then whether it's polar or nonpolar. So let me blow this up a little bit. So let's take a look at first SeH2, so selenium dihydride. And the first thing we want to do is find out the total number of valence electrons. So selenium is actually a group 6A element, so it brings 6 electrons. So we'll put a 6 there. And we have 2 hydrogens, and we know that hydrogen brings 1 electron, but if we had 2 of those, so that's a total of 8 valence electrons that we'll be working with. When drawing the structure out, always ask yourself, who will be the central atom? Well, hydrogen will never be the central atom, so we can put selenium in the middle. And then put the hydrogens on the outside here, just like that. We have 8 electrons, so again, satisfy the external atoms first, your outside atoms. So we have the hydrogens bring 1, the selenium's going to donate 1, so the hydrogens have 2 electrons. Now recall that hydrogen can only have 2 because hydrogen is in that first row that only has a 1s orbital, so we can't give it any more electrons. Don't try to. And never make hydrogen a central atom. So we have 4 electrons represented. We need 4 more, so place the other 4 on the central atom. All right, and now the next thing that we want to do is actually find out what is the name of the geometry with the lone pairs. So here's our shape. And again, going to the table, we have to ask ourselves, what is the potential for this element? Or this compound, I'm sorry. So again, potential is defined as the number of external atoms, so we have 1, 2, plus the number of lone pairs that's on the central atom. Again, the only lone pairs that are on this compound are on the central atom, but never ever consider any electrons on any of the outside or external atoms. So we have 2 lone pairs of electrons on the selenium, and so that means that we have 2 plus 2, which is 4, so that means that we will work out of column 4. So the name with the lone pairs is tetrahedral. And then the shape that the atoms alone form, that will actually form a bent shape. How did I get that? Well, again, once you determine what your potential is in column 4, we're going to stay in column 4, but we'll use this information over here to help us determine what the shape of the molecule is. So if I have 2 lone pairs, come on over, and the name is bent. Now let's take a look at that if we can. Let's write that down first so we have a bent shape. Alright, so looking at this shape here, we have a tetrahedral shape with the lone pairs and with the 2 atoms. However, when we look at this shape, again, how we're referencing it is not necessarily in a straight line. This is not a linear shape, but we have our atoms aligned like this if we were to draw it on paper, but when we bring it to the 3rd dimension, we can actually see that this is not 180 degrees away from each other. Now, the next question, or the last question, is whether this is a polar or nonpolar molecule. And I like using the analogy of the tug-of-war analogy, or that all the horses are pulling here. If you have lone pairs in the analogy don't push or pull. However, if you have atoms and they're able to push, these are not completely opposite of each other. So these will push and the central atom will move. So this is a polar molecule. So if I were to ask you a follow-up question, would SEH2 dissolve in water? Your answer should be a resounding yes. So this is a polar molecule. Okay. Now, what's also neat, and I'm not asking you to discuss this, but we also have what's called polar covalent bonds between our central atom and the two hydrogens. So the selenium, and wherever we see these sticks, that represents that we have a shared pair of electrons. So we have a polar covalent bond, and this is a polar compound. Now, at times, we can have polar covalent bonds between molecules, or I'm sorry, between atoms, and have it be a nonpolar compound. And we'll show an example like that, hopefully. All right, so let's take a look at the next example, or next question. Here we have a polyatomic iodate, IO3 with a -1 charge. Okay, so let's do the first thing. Again, get the number of valence electrons. So iodine brings 7 electrons. How do I know? Because it's over here, group 7. So 7 valence electrons. And then oxygen, each oxygen brings 6 electrons. Again, here, group 6A. So plus, and we have 3 of those oxygens. So 6 electrons. Now it has a -1 charge. The -1 charge indicates that some metal gave this structure an electron, so we have to add 1 electron. So when looking at this, we have essentially 18 plus 8, which is 26 electrons. Okay, so that's our total. All right, ask yourself, who is the central atom? Well, we only have 1 iodine, so let's put it in the middle. And then we'll put our 3 oxygens around it. Okay. Let's go ahead and satisfy the external. So give our outside atoms what they want, which is 8. Okay, so right now we have 24 electrons, but we need 26. So whatever's left, dump on the central atom. Okay. Now, if we had, say, 28, we would not want to stack them up on top of each other. We'll give them arms or legs or antennas, whatever you want to call it, but we'll have an example for that a little bit later on. And then, of course, since this is a poly, you definitely want to bracket the whole thing in, and it's a -1 charge. So it looks like we have our correct Lewis structure. All right, now the next thing that we want to ask about this is, what is the shape that this forms with the lone pairs? So first of all, we have to determine what our potential is. So how many external atoms do we have? Correct, we have 3 plus 1 lone pair. So that means that we are looking again in column 4. Okay. So we have a tetrahedral shape. This is our basic shape, or our most fundamental shape, that if we had another oxygen on there, then that would form definitely a tetrahedral shape. But we do have 1 lone pair. So when looking at the shape, again, stay in the same column. So we're in the column 4. We have 1 lone pair. So this forms a trigonal pyramidal shape. Okay. And let's take a look at that. So here is the shape. Looks very similar to the last model, except now we have 3 external atoms and 1 lone pair. So when we look at this, it does form kind of the tetrahedral shape, but notice that this central atom is not on the same plane. It doesn't lie flat with the other 3 atoms. So it forms a trigonal pyramidal shape with that basic tetrahedral. Now the last thing I want to ask is this a polar compound? Well, again, these all do not lie on the same plane. So if we were to add up all of the forces, quote unquote, that's pushing on that, it would cause it to move. So this too is a polar compound. And this polar compound would also dissolve in water, since water is polar as well. All right, let's take a look at the next one, or another one. Here we have ICl3. So when looking at ICl3, again, let's get our number of valence electrons. So iodine, again, is in group 7. So it has 7 valence electrons. And And then we have three chlorines, and chlorine is also in group 7. So that means we have 3 times 7. And in this case here, we have 21 plus 7, which is equal to 28 electrons. So we do have an even number, but it is a strange number. But that's okay. So let's go ahead and draw our Lewis structure. So place iodine in the middle, and then place the 3 chlorines around it. Go ahead and satisfy the external atoms. Give them their 8. And right now we have a total of 24 electrons, not 28. So we need to add 4 more electrons to this structure. But what we do not want to do is that. Don't ever put more than 1 pair in the same quadrant. So in this case, we're not going to put 4 there. We're going to actually give it antenna, so to speak. Okay. So what this is representing is, yes, iodine is bonded or is sharing 3 pairs of electrons, which is 6 electrons, and then itself it has 2 more pairs or 4 more electrons. So it is possible for iodine to have 10 electrons that it's working with or sharing, combination there. All right, so let's take a look at the name here. So first of all, what is the potential? Well, we have 3 external atoms plus 2 lone pairs. So again, 3 plus 2 is 5. So our basic shape name is trigonal bipyramidal. So we have a, trigonal bipyramidal. Okay, so trigonal bipyramidal, and then we have 2 lone pairs of electrons. So again, staying in column 5, but we have 2 lone pairs, so zip on over, and we are forming a T-shaped planar, which is kind of neat if we look at this. So a T-shaped planar. And I think I may have done this example in class, but if you were to draw the lines, what is that green form? It's a T, and it's kind of nice that when we look at our shape here, okay, this is a trigonal bipyramidal shape, and if we have 2 lone pairs of electrons, in this case here, now it forms a T that has those 2 lone pairs of electrons. And the last question I want to ask is this a polar compound or a nonpolar compound? So again, you have your 2 pushing in opposite directions, but we have this 1 down here pushing up. And again, remember that lone pairs don't push or pull, so it does cause the central atom to move. So this also is a polar compound. And yes, that would too also dissolve in water. All right, let's take a look at the next one. I3 with a -1 charge. Okay, kind of an unusual one. So we have 3 iodines, and again, iodine group 7A. So 3 times the 7 electrons, which is going to give us 21 electrons, but since it has a -1 charge, that number there should be a red flag, so we're going to add 1 electron for a total of 22. Okay, so we're going to work with 22 electrons here. So the central atom, take your pick, it's iodine. And I'd go ahead and put them right in a row. Don't try to do anything fancy with it. Now, there's a difference here of external atoms and a central atom. This is a central atom, these are external atoms. We can't just jostle them around, and they don't move around either. So we have to treat them as if they were external atoms by giving them their 8 electrons. Okay, so again, give your external atoms what they want. And in this case, we have a total of 16 electrons used up, but we need to show 22. So I can put 2 more there, that's 18, so I need 4 more. So I'm going to go ahead and put a pair here and a pair there. So when looking at this, it is true that this iodine has more than 8 electrons, but it is a central atom, whereas these 2 iodines are external They can only have 8. So what you don't want to do is put another pair of electrons in there. That would be bad. That would give this iodine 10. And you might say to yourself, well, the central one has 10. The central one can have 10. But as an external, it can only have 8. All right. So let's take a look at this and ask ourselves, well, what is our potential here? So we have 2 external atoms plus how many lone pairs on this? And again, only focus on the central atom. That's the only one we care about. We don't care about this one. We don't care about that one. So we have a lone pair of electrons down here in this quadrant, and we also have 2 pairs up here. So we have 3 lone pairs plus the 2 atoms. So that gives us a potential of 5. So the shape, the generic shape, or the basic shape, is trigonal bipyramidal. Okay. So we have a trigonal bipyramidal shape. Okay, so it's trigonal bipyramidal, but now what shape do the atoms alone form? Well, we have 3 lone pairs, so we are in column 5, and we come down here to where it says 3 lone pairs, and in this case it forms a linear shape. And it does form a nice straight line. So when we look at that, zap that. So we have a linear shape. And let's take a look at that model real quick. So again, we have our 3 lone pairs. So when we look at it, we have this shape right here, and we have our 3 lone pairs around the central. And you always take them around from the trigonal bipyramidal around the central axis, so that these 2 are 180 degrees away. And the way that I have it drawn, I have the 2 lone pairs on top, the 1 lone pair on the bottom, and these 2 iodines opposite each other. Now, the next question I want to ask is that a polar or a nonpolar compound? And hopefully you're saying that that is nonpolar, because again, the lone pairs do not push or pull. These 2 atoms here are pushing in with the same amount of force, plus, since these are all the same atom, these are nonpolar covalent bonds. So there is no greater attraction, or you may hear me use the word dipole moment. There are no dipole moments in this structure. So this is nonpolar for a couple of reasons. The main one is the shape. So this is a nonpolar molecule. All right, let's take a look at the next one here. RnCl4, so radon tetrachloride. Radon is a noble gas, which is okay, because once we get to these bigger noble gases, notice it's not even in the picture down here. Radon's way down here. It's a huge noble gas. And you can make compounds with these larger noble gases because, again, those electrons get farther and farther apart away from each other. Elements can sneak in and make compounds, or we can make compounds. It's no big deal. But we want to keep track of the electron amount. So the radon brings 8 valence electrons. Yes, we still consider that. So we're going to have 8 electrons from the radon. And then chlorine, each chlorine, again, brings 7 electrons, and we have a total of 4 of those. And there is no charge on this, which is kind of nice. So we have 28 plus 8, which is 36 electrons. Okay, it's an even number, but it's a good number that we can work with. So let's go ahead and put the radon in the middle. It's our central atom. And then go ahead and put your chlorines around. Give them their 8, just like normal. Okay. So right now, we have 32 electrons represented, but we need to show 4 more. So this is a great opportunity to do that. Now, I like doing that opposite each other, not necessarily going this way, but you could actually swing it over in that way if you wanted. But this kind of is nice because once you have this drawn out and you know the names and the shapes, it actually kind of draws out the shape that it actually is forming, that the atoms alone are forming. All right, so let's ask the question, what is the potential for radon tetrachloride? Actually, let's scoot that over a little more. In other words, I have 4 external atoms plus 2 lone pairs. Very good, total of 6. So we're working out of this column right here. And the first name that we have on there is octahedral. So we have an octahedral shape. But we have 2 lone pairs. So the shape, again, we're working out of column 6, go down 2. So it forms a square planar shape. And I'll show this shape here in a moment. So it's a square planar. Okay. So let's take a look at that. So here is the shape, the radon tetrachloride. So again, it has the 2 lone pairs of electrons on either side, and we have our 4 chlorines around it. And notice how it forms that nice square shape that also lies on a plane. So that's how we get our square planar shape. Now the reason why I like drawing it like this is if you were to connect the dots, it kind of forms a square on the side. If I hold it kind of like this, you can actually see that little diagonal action there. But again, it's a nice square planar. Again, you have to pretend that you're looking at it on the slant, where this one's coming out and that one's below. So, last question on this one, is this polar or nonpolar? Take a look at it. So we have a square that lies on a plane. All of the atoms are 90 degrees away from each other. This lone pair and that lone pair don't push or pull. Very good. It is nonpolar. This is a nonpolar compound. So in this case, this would not dissolve in water because it is a nonpolar compound. But it might be good at taking paint off of your paintbrush since it's nonpolar. All right, let's take a look at the next one here. HBF2. Oh, there's boron again. All right, so let's get our numbers first. So we have hydrogen, which is 1, boron, 3, fluorine, 7. So we can get our numbers. So hydrogen, 1 electron plus 3 electrons plus 2 times 7 electrons. So now we have 14 plus 4, which is 18 electrons, which is kind of interesting. So let's go ahead and decide who our central atoms are. So boron obviously goes in the middle. We have a fluorine, and a hydrogen. Okay. So we have 2 fluorines and 1 hydrogen. Let's satisfy them. So make sure that gets there 8. And how many electrons are represented here so far? 8 plus 8 is 16 plus 2, which is, 16 plus 2 is 18, my bad. And there are no other electrons, and remember, boron is a moron. It does not want an octet, so we are happy with the way that this looks right now. So don't swing it a pair over. Boron only wants 6 electrons. Okay? But that doesn't change our fun in naming these things. So let's scoot that on over. So first of all, what is the potential for HBF2? We have 3 external atoms plus no lone pairs. Therefore, we are looking at a trigonal planar shape because our potential is 3. So we'll go trigonal planar. And since there are no lone pairs, then the name has to be the same. So this time we have the names the same. And yes, do write it twice. All right, now let's go ahead and get this structured. All right, so I don't have a model ball that is able to do a trigonal planar with 3 single bonds. So I'm going to use this, and we're going to pretend that these lie on the same plane because I don't have a representative for boron. So these 2, blue, represent the fluorine, and this one represents the hydrogen. The reason why I want to show this is for whether or not the molecule is polar or nonpolar. is this a polar or a non-polar molecule? Because they are. They're all equally spaced out at 120 degrees away from each other. Is this polar or non-polar? Very good. It is polar because we have different external atoms. Anytime you have different external atoms, it is automatically polar. Don't even think about it. Don't even try to talk yourself into it. In other words, trying to say, oh yeah, well, if it does this. No, because I'm going to try to trick you on one here very soon, and you better not fall for it. All right, let's take a look at the next one here. Actually, the last one. So this must be the one I'm going to try to trick you on. So we have CH2Cl2, so let's get our electron count. So carbon again brings 4 electrons, and if you're not sure about that, carbon again is in group 4A. Each hydrogen brings 1, and we have 2 of those. And we have 2 chlorines, so 2 times 7. So we have 14 plus 2 is 16, so we have 20 electrons that we're working with here. Again, put carbon in the middle. And I'm going to put the chlorines over here. I'm going to put the hydrogens. Oh, let's not use that color. Actually, no, let's not use that color. Let's use a different color. Let's use that color, whatever that is. Gray. Gray, yummy. All right, so again, satisfy, give them what they want. Okay. So we have 8 electrons on each chlorine, which is 16. Add 2 and 2, so that's a total of 20 electrons. So there's our structure. Okay. Let's focus on, what is the potential for this molecule? Very good, it is 4. So we're going to name it a tetrahedral shape. And since there are no lone pairs on the central atom, the name is the same. Okay. Now, I'm going to try to talk you into this. Look at this shape. If I'm not sure if this is polar or non-polar, or if this is polar compound, because if we look and we see that, okay, the carbon's pushing this way and that way on the chlorines, and the hydrogens are pushing this way and this way on the carbon, don't those forces kind of cancel each other out? Well, the answer would be yes if it were a 2-dimensional structure. This is not 2-dimensional. This is a 3-dimensional structure. So when we look at this, let me actually pop that on there. We can use this model to represent what it is that we're drawing. So we have the chlorines here and the hydrogens here, and notice that these are not opposite each other. If I hold it like this, it kind of looks like they are, but then once I bring it to the 3-dimensional plane, we can see that the chlorines are like that. And some of you may have said, well, I kind of drew them so that I had a chlorine here and a hydrogen here. Doesn't change anything. Doesn't change anything. It's still a polar compound because, again, it's a 3-dimensional shape, not a 2-dimensional shape. So this is a polar compound. Polar. Hope this video was helpful. And again, we're going to have some more practice, and test is coming up soon.